there are two major advantages of the digital processing. One is, as already mentioned, flexibility, and the second one is reproducibility, or in the flexibility, you can think of the same machine, that is the hardware to be used, and with modification of some portion you can obtain different behaviors from the same system. And the repeatability is that the parameters do not change with respect to time. You can think of the capacitor or an inductor or even the resistor with respect to the time, or with respect to various physical parameters like the temperature or other conditions, the parameters will start varying. That variation in parameters will obviously affect the behavior of the system. So, this is in a nutshell the signals and the systems being operated upon. So, the signals and systems course will have a discussion on the following. So, first one is the representation of the system as well as the signal. So, the signals can be represented in different ways, systems can also be represented in different ways. Each representation has its own merits and demerits. So, we will look at such representation, basically the mathematical representation. It can be block diagram, it can be in the form of a waveform, and so on. So, this is one representation that we shall look at, and then the transformation of the signals. So, the signal which is in time domain can be transformed into the frequency domain, and it can be again transformed back to the time domain. So, this representation, this kind of transformation will help us in simplifying some of the operations that are tedious in time domain or vice versa, and using the both the domains well. Okay. So, time domain as well as frequency domain. So, by this time I think you are you would have recalled what is the tool that we are going to use. So, we will be obviously using the Fourier analysis. So, either the Fourier series or the Fourier transform, depending on the type of the signal. So, this representation is one part, then the transformation. We also will look at the Z transform in one of the modules. This representations, along with the advantages of digital systems, will ease a lot of burden on the end users, so that we are able to quickly decide the further course of action in any given situation. So, for that I can again recall the fire alarm system here. So, we may not be directly be talking about the fire alarm system, or maybe the burglar alarm, or such systems all around us, even the tsunami alert systems, or it can be the seismic earthquake alert systems and so on. We may not be directly talking about them as a case studies also, but we will definitely be hinting at the scenarios that are actually faced by these systems, and the whole representation of the systems is going to be studied in detail with the understanding of these subsystems in general. I would like to continue the discussion on the signals and system with the classification classification of the signals. So, the signals can be classified in varieties of categories. First, we shall just look at one basic classification, which is called as continuous time and discrete time systems. So, in both these cases, this first classification is going to be based on the time. Please recall, I represented one of the voltage as something like V of t equal to say 35 sine of 50 pi t, right. So, this was the voltage that we mentioned at the beginning of the class. So, this representation is assuming that the time is an independent parameter and the voltage is being represented as a function of the independent parameter, that is time. So, if this t is, if this parameter is a continuous function of time, such signals are called continuous time signals. That means these signals are defined for all possibilities of time. Okay. So, if you were to plot such a signal, then you can see that the signal can be represented this way as a sinusoidal waveform. So, this, if you were to enlarge over here, then this is 0, this is pi, this is 2 pi, and the amplitude over here is the maximum value, that is 35. So, this is the voltage V of t. This particular signal, the signal has been represented or it has been defined for all values of the time variable. So, if you want to find out the current the voltage at say t equal to 0.1 seconds, all you need to do is just substitute that V of t in terms of in place of t, you can substitute 0.1 and you get 35 sine of 50 pi into 0.1 and you get some value of voltage over here. Suppose if you want the other values, like if it is t is 0.001 or 0.0011 or 12 and so on, any values of t, you can definitely find that corresponding value. So, this has been defined. So, each of this time will have a certain value. So, it can be going all the way positive or negative. So, this kind of signals are called continuous time signals. So, one such representation, one example that we can think of is a random. So, this signal that has been represented over here in this graph, I can think of it as a signal which is having some mathematical relation like 35 sine of something or maybe 0.1 cosine of 30 t and so on. There can be other signals also which are not having any particular mathematical representation, but which do have the waveform this way. So, this kind of representation, if you were to see, this is also starting from some negative time over here and going on in the positive time and with respect. So, the amplitude is continuously a function of time and it is continuously varying with respect to time. So, this is one more such example. So, the difference between the first waveform and the second waveform that you see is that the first waveform is possible to mathematically describe, and once you are able to mathematically describe, you can substitute this value and then determine the corresponding value or do some operations like integration or differentiation on the given signal. But on the other hand, the second signal that you are seeing is more random in nature, random in nature. So, the suitable word for the first can be then deterministic, deterministic in the first case. So, the random signal is obviously varying in a random fashion, and you cannot or you do not know its value until and unless that event has actually occurred. So, this can also be one more classification of the signal. So, that is random signal and deterministic signal. So, whenever we are converting any physical quantity in real world using a transducer, we get these signal. They can be deterministic or they can be random depending on the system. Now, if this kind of signal were to be sampled, if you were to take the samples of those signals, then you will get the next representation, that is called discrete time. So, the D over here stands for discrete. Discrete means they are not defined for continuous values, but they are defined for some separate and distinct values. I can separate or distinct values, distinct values. So, dictionary meaning can also be looked upon like a discrete. So, discrete time means separate times or distinct times. So, here you can think of taking the samples over here, right. So, instead of noting down or instead of finding all the values, I can just think of noting only the parameters at discrete values of time. So, these are the values which, so the dots over here are actually representing, and if I were to plot it, so I will get something like this. Okay. So, this is our representation of the same signal which is shown in the first graph, but with only the discrete values. Now, you can see that the moment you take only discrete samples, what happened to the samples in between? Suppose these two values. So, this is say time instance, this is 0, this is 1, 2, 3, 4, 5, 6, 7, 8, 9 and so on. So, this variable over here can be represented as n. Okay. So, by convention the discrete time is represented using small case n and continuous time is represented using small case t. So, I want you to concentrate on the samples and the space between the samples 4 and 5. 4 over here is the index value, 4 or even 5 is also index value, 4 or 5 are the index value, and the sample value is this highlighted one. So, I have made it a bigger blob over there. So, the highlighted version is highlighted values, they are the amplitude values. So, the same values are present somewhere over here this way. Okay. So, these two values have been defined at discrete time instances, that is 4 and 5. What is there between 4 and 5? At 4 you have certain value, at 5 you have certain value. So, it depends on whether you are talking about the x of n or x of t. X of t can be the continuous time version, x of n if it is the discrete time version, then x of n is not having any values, any sample values between 4 and 5. So, it has the values are defined at 4 and the next value is defined at 5 only. So, this is separate, these are distinct values of signals that you have. In between 4 and 5, there is no signal, there is no amplitude defined. On the same lines, this continuous time signal will have not only the value at 4 and 5, but even between 4 and 5 also all the values are defined for this continuous time signal. So, you can in general think about this whole signal being a small duration signal, maybe for 1 second or so, or maybe 1.5 second, or say a small signal like some noise that you captured using your smartphone and you have recorded a MP3 signal. So, this can be one actual signal that has happened, and your transducer in your smartphone could capture this one. So, using this you can reconstruct the signal and you can play this signal on the system, on any of the, say you can play back and you can observe the difference. So, when you record, you are actually recording the happening in the real world, but only discrete values are noted. So, this is the first classification that we have, that is continuous time and discrete time. So, obviously, how this discrete time signal is obtained? So, discrete time signal is obtained from x of t. So, you are going to replace x of t, the t is replaced by something called tau into n, right. So, you can have the tau where you can say tau is the sampling period, okay, and you can consider n as an integer anywhere in the range of minus infinity to plus infinity. Okay. So, you get the samples. So, this is the sample and this is the signal that you are getting. Where do we come across this kind of discrete time signals in real world? Definitely you would have come across some situation wherein you may have to report to a doctor about the temperature of a patient. For example, someone elderly in your home maybe has a fever and you want to report to the doctor about the daily condition of the elderly. In that case, obviously, you can think of a situation of noting the temperature for one whole day. So, how that would happen? So, I can plot a simple graph over here, where this starting point represents 6 AM, then comes somewhere around 12 noon, and then evening 6 PM, and midnight 12, and again back at 6 AM, right. So, this way, excuse me if I have marked the duration non-uniformly. Yeah. So, now I have made a small correction: 6 AM, 12 noon, 6 PM, again 12 midnight and 6 AM. So, if you were to note down the temperature of the patient, right, you will in the morning you can note down some value, say the value will be something like this, and by 12 noon maybe the temperature has increased a bit. Then again by evening there is some small variation and it has dropped, but midnight again there is some variation, and again in the morning there is a difference over there. So, if you were to look at the temperature over here, right. So, this is actually conveying a lot of information about the health of that patient. The doctor can look at this waveform, or he can look at all the values that have been supplied over here to him in the form of just a table over there, and he can definitely decide about the condition. So, whether it is stabilizing or whether the temperature is fluctuating. So, what type of medications to be given, whether it could be a viral fever or if something else, right. All such information is to be extracted only by the doctor. So, only doctor can do that information, but you can definitely note down these values. Now, what does this mean? Does it mean that the temperature is measurable only at 6 am and at 12 noon? In between there are no such values? Not precisely. So, definitely the temperature are present somewhere like this, right, but convenience wise you have noted the values 4 or 4 samples per day. Now, if you were to increase the frequency, so after 6 am, suppose if I were to note down the temperature at say 9 am, okay. So, 9 am you will get more samples. So, after 12 noon somewhere at 3 pm again I will note down one, then after 6 pm one more sample at 9 pm, and again early morning say again 3 am. So, 3 am, 9 pm, then 3 pm and so on. Now, you can see that the waveform will take a bit modified shape, right. So, if you were to connect all these, so it will take a bit different shape. Number of samples have increased. Only thing is that you have taken the samples at discrete time instances. So, I can mention these values as discrete or separate or distinct time instances. So, the samples have been noted at discrete time instances. Obviously, all these samples are at equidistance. Okay. So, I can also write equidistant samples, from one another. So, there is a gap of 3 hours between any two samples, right. So, this is our example for a discrete time signal. So, these discrete time signal is actually therefore a sampled version, sampled version of continuous time signal, sampled version of the continuous time signal. Let us see how do we represent these signals and what operations can be done in this one. So, you can consider a signal like x of n. Okay. So, x of n is signal like 2, 4, 1, minus 2 and 5. This is the signal, right. Can we plot this and observe how this variation is happening? So, for that I will consider the x axis where n is mentioned and y axis will be the x of n. So, the origin is over here. I am going to mark discrete time instances like 1, 2, 3, 4, 5 and so on, and I am going to plot the values over here. So, this can be 1, 2, 3, 4, 5 because I am seeing a maximum value of around 5 over here. So, this is the amplitude. So, what does 2 indicate? The 2 over here indicates the amplitude of the signal at that particular time instance. If nothing is mentioned, we have to consider the first value as the origin. Usually, the origin is also marked with a small arrow as shown over here. So, this arrow marks the origin. Now, let us try to plot this signal. So, look at this one. At 0 the value is 2, right. At 0 the value of the signal is 2. Similarly, after 0 this is 1, this is 2, this is 3, this is 4. So, at 1 the value is 4, this is 1, 2, 3, 4. this is the signal. Similarly, the value at 2 is 1, this is 1, okay. The signal can be plotted like this. Then the value at the time instance 3 is -2, so this is -2. Then the last value is 5, so the 5 can be represented like this, okay. So this is the representation of the given signal. I want to write it like this: x of n is 2, 4, 1, -2 and 5. It means that this is x of 0, this is x of 1, this is x of 2, this is x of 3, and similarly here it is x of 4. Usually we have the signals that are represented. For understanding purpose, we will have say 5 or 6 or 8 samples in it. But frankly speaking, the signals that are emanating from a natural source like the ECG signal or the EEG signal or varieties of other signals, they will have millions of samples, and it also, again, as I mentioned earlier, depends on the sampling that you are doing. The temperature example, how many samples have been taken? For every 3 hours you are taking one sample. So in a day of 24 hours you will have these many samples mentioned: 1, 2, 3, 4, 5, 6, 7, 8. Okay. Again the next day this comes, this 6 am is again the next day's sample. So you will have 8 samples if you are taking a sample every 3 hours. Now just imagine if you are sampling, if you are taking 10,000 samples per second, right. So per second, if it is 10,000 samples or 12,000 samples, then you can just imagine the number of samples that will be there in a given signal. Now as and how I am speaking over here, my voice as well as the video is being captured by high definition systems. You can imagine how many samples would be required per second, and if it is a lecture of say 20 or 30 minutes, then you can just calculate simple mathematics, and you will realize that the number of samples will be in millions for one such video. So many millions of signals are there, then why are we just talking about this signal which has hardly around 5 samples here. So this is for our understanding purpose. So plotting those millions of samples and doing any operation on that, addition of such and multiplication will be very cumbersome. So we will try to understand throughout this particular course, we will try to take these kind of simple examples and then understand the whole intent of the operations to be performed on the signals. Okay. So this is the first classification. Let us also take a small variation in the above example. So instead of x of n, so being 2, 4, 1, -2 and 5, instead of the origin being at 2, if I were to have the origin at say 1, then how the plot will be. So in this situation what happens is, this is x of 0, the arrow mark over here indicates the x of 0, okay, arrow mark indicates x of 0, and obviously this is x of 1, and this will be, the last one will be x of 2, x of 1. So what is this value then? What is, how do you indicate 4? So the 4 is nothing but x of -1. Similarly 2 will be x of -2. So let us quickly plot this graph here again. Now you can see the difference. This is x of n, the same signal, but the origin is now not at the first value, but at the value over here, say like the third sample. So this is 0, the 1 here, 2 here, 3 here, then -1, then minus 2. So, what is this? This is at minus n, negative n. So, if I were to plot the sample here, let us begin by say x of 0. What is x of 0? X of 0 value is 1. So, this is 1. Okay. Similarly, what is x of 1? X of 1 is minus 2. So, where is the location 1? So, this is x of minus 1. So, this is minus 2. X of 2 is 5. So, x of 2 will be this value, that is 5. Okay. So, this is 5. Then we have x of minus 1 is 4. So, 4 can be represented over here. So, this is 4 and this is x of minus 2 is 2. Okay. So, what is the difference between the first representation and the second representation? You can see that it looks like the signal has this signal has moved to the left, right. So, the signal has as though it has moved. Okay. So, this is also going to be one of the type of operations that we will in the further classes do operations on the signals. Okay. So, I will be taking these examples for further classes also for classifying the signals and understanding the concepts well.